All right, so we're going to get started learning about Codewarrior 10.3 and how we use it with the Freedom Board. The goal of this video is to show you how to get started from what I would consider scratch. Um, you might have loaded a precompiled application, or some of the demo code, but this is how, if you want to start from scratch, make it just a raw program, nothing else. So on my desktop, I have Codewarrior 10.3 installed. And this is the special edition. You get 128K of code. This is what you want. The other thing you probably want to have on hand is kind of all the stuff for the Freedom Board. You can go to the Freedom Board website, get the pinouts, user manual, schematics. Quick start package is useful. Now, before we get started with Codewarrior, what I need you to do is make sure you have the right firmware on your Freedom Board. So there's what's kind of cool about the Freedom Board. It has this open SDA interface that allows you to have a couple different ways of getting code on the device. Out of the box, it has this mass storage class programmer, and it's pretty simple. You plug it in, it shows up as a thumb drive, and you drag and drop S records, binary files. Now, for all the tutorials I do, we go at a little bit lower level. We want to run a debugger. So there is, and some instructions on how to, enter the bootloader mode. So you can kind of change the SDA application from the mass storage class to the bootloader. You can read the instructions, but what we need is in the quick start package, there is an application called Debug App PE Micro. So what this gives us is a way, let me get up my device manager here, to do debugging, through the single wire debug. So, interface on the ARM, on the Kinetis. Whenever you have everything installed, it shows up as PE Micro Open SDA Debug Driver. There's a lot of cool things you can do with a real debugger. The other thing you should see under your ports is this virtual COM port, this communications class device. Now, that being said, let's get started. So if you've never used Codewarrior before, let's just click on it. Codewarrior, Codewarrior 10.3 is based upon Eclipse. Eclipse is an open source framework used by a lot of tool vendors to kind of build IDEs. So a lot of people use it. You can go to other vendors. You'll see they're also using it. So the first thing when you start it up is that Eclipse needs its workspace. By default, I kind of have a workspace already ready to go, but you can kind of put it wherever you want. So what I'm going to do is I have a D drive on my machine. Oop, not that. D drive. Make new folder. I'll call it Freescale Demos or something. This is where you'll see in your workspace all of your kind of parameters are stored. Projects can actually go here and code can go here, but they don't necessarily have to. But we do need a workspace, so we'll click OK. The splash screen's on my other monitor, so we'll give it a minute. So if there's nothing in your workspace, you kind of come up with this screen. So I'm going to blow away the welcome screen and get to our workspace view. So in Eclipse, on the left, we have our projects view, which I can't really, there's no projects. They have this new in 10.3, this commander view, which kind of reduces down all the different Eclipse functionality into a couple, simple operations. My main area, this is where the text editors and whatnot will go. We see code, and at the bottom, there's a console, another little window. So for our Freedom Board, what I want to show you is with nothing else, we just want the most simple project. That's the way I always start. I don't like code auto generators. I don't want any of that stuff. I want to see how you make the most bare basic project. So we're going to go to We can do it from the commander, but I'm going to show you without the commander. So we go to File, New, and here's what we want: a bare board project. We don't want MQX, none of this other stuff. We want a bare board project. And what that means is just that. If you were to make your own circuit card, this is what you do. So I'll have a project called Getting Started. And you notice by default, it puts it in where we had our workspace. And I'll show you in a minute, it doesn't necessarily have to be, but we can put it in the workspace. We click Next. Now we have to choose our processor, so Kinetis L, 2X, we're in the KL25Z. I know this because I looked at the data sheet or the schematic for the Freedom board, and it's this device, the Z128. We are making an application. We are not making a library, although you could. The next important thing by default it doesn't come up with, I don't have on hand the multi-link universal pod, but we have an open SDA interface. That's what's on our board. Language is C. Floating point, there is no floating point unit built into the M0. The M0 Plus core that's in the K0 or the KL device, KL25. So it has to be done in software. I/O support, we'll talk about this in another another tutorial. Just leave it alone. And here's the other interesting part, is that as of 10.3, all the Kinetis, the M0 parts, they don't use Freescale's compiler. They use GCC, just the open source GCC compiler, which is kind of cool. So we don't have even the option to choose Freescale. And that will have some interesting side effects. In some other tutorials I've done with the Quick Stick, and I believe I did it with 10.2, it was all Freescale's compiler. Now the only difference are some of the startup routines. There's some minor differences in the startup routines in the interrupt table, which we'll look at in a little bit. Now Freescale also has, part of Codewarrior, some tools that allow you to quickly initialize the device to make some auto-generated code. This device initialization and processor expert. We're not going to use any of that. I want the barest of the bare. So we'll click Finish. It's going to think for a minute. And so over on the left here, I have my project in this workspace view. So I'm going to expand it, called Getting Started. We have one configuration. There are things called build configurations in Eclipse. We only have one called Flash, and you can kind of define different build configurations. A good example of why you'd use this, maybe you want one where you locate all of your program in RAM. So a lot of the other Kinetis for, say, the K40, the K20 projects do that out of the box. Give you a couple build configurations. We only have one here. And there's a couple default, folders here. And one thing I'm going to bring up is, let me, on another monitor, bring up my folder. Let's look in our Freescale demos in our workspace. There is a bunch of metadata about the whole workspace in here, but you also see my project. And you notice whatever folders I kind of see in here, I see over here, except for some of this metadata about the project. It actually mirrors the file system. So if you see something in sources, it really is in the file system. And I can right click and go show in Windows Explorer. It brings it up. If I delete it in any one place, it goes away in both. So be careful. So looking at these folders, we are essentially looking at a part of the file system. There are ways to link in code. So what you would see in here are references to other places in the file system, but for now we don't have that. So when when Codewarrior starts a new project, there's a sources folder that has all your C code that it generates. It generates a little main.c. It generates another file. I'm not going to talk about this today. It's used for a trace buffer for debugging. Just leave this alone for now. Don't do anything with it. It generates a main.c. We'll look at here and we'll talk about it in a minute. There's this project headers where it pulls in Yeah, it's a big file. It pulls in a nice header file that has nice macros for all the registers. I'm going to make a completely different video talking about how to use this. But for now, it's here. There's another file I'll talk about in a minute, derivative.h. Lastly, under project settings, this has some interesting files I want you to be aware of. One in startup code. Whenever a processor boots, it jumps to the reset vector. In an ARM, there is a reset vector, and we'll look in a future videos talking about interrupt vectors. But before it gets to your main routine, there's startup code that kind of sets up the C environment, initializes stack, initializes variables, and whatnot. You don't ever have to mess with any of this. Just leave it alone. But there is one file called kinetosysInit that does a little bit of stuff before, when we boot. So now you won't, if you're not an expert in C, don't worry about it. I'm going to go through this and just show you what you need to know. So this init hardware gets called in the startup routines. But what I want you to do, you can look up these registers and see what it does. But the first thing it does do, there is this a register that points to the base of the vector table, in the ARM core. And by default, it's set at 0, and it relocates it here to a place called vector table. It's just a symbol, and if we look far enough, we see, oh my gosh, here it is. The vector table is defined down below. Now there's all this stuff here. For now, don't worry about it. All this does is makes an array, an array here called interrupt vector. Constant means read-only. And it creates an array of function pointers. All a function pointer is essentially an address to a function. And this stuff here is just saying, all right, it's putting it a special place. It's telling the linker to put this in a place called vector table. And in here are just lists, are just functions. All right. Thumb startup. It turns out the first location of the vector table is actually the location of the default stack. But thumb startup is the first thing that gets called. And the rest here, it populates these with names of functions for the interrupt vectors. Now, what's cool about the way they have GCC set up is that by default, they have some symbols set up for all the default handlers, and they're set as weak symbols, meaning we can override these later. In the tutorials, we're going to talk about how do we do interrupts, for this processor and the Freedom board. We're going to reference this again. I just want you to point this out. It's here. An interrupt table's already set up and kind of ready to go. So let's jump out of that. There's some runtime configuration. You don't need to play with any of this stuff. But so let's just go to what we really care about. Actually, before I do that, let's look. There is a linker command file. This is a file that tells the linker, where memory is at for this particular, for this, the KL25Z128 variant. And it kind of defines how big the stack is, where ROM is. And you notice here's the vector table. This tells the linker where to align everything. So as you kind of get good with compilers, you'll be able to look at this. It looks kind of goofy if this is the first time you've seen this. But it's actually in the end pretty simple. It's just telling the linker where all your code's going to go, because different chips have different amounts of memory and whatnot. So let's jump out of here and go to what we really care about, main.c. So Codewarrior forever, even before his Eclipse, always included with a new project this thing called derivative.h. So it's derivative.h is just an include file that points to another include file for your chip. So if you include derivative.h, it kind of gives you all the stuff you need, some convenient stuff for your chip. But you notice what it does, it just includes this other header file for the MKL25, which we discussed before. Now I'm going to have another tutorial on how we use this file, but suffice to say, all it is in here is all of the macros for talking to hardware, like here's stuff for the timer, timer pulse with modulator, UARTs. So we'll come back to that. Main.c, we include that. Now, this first demo doesn't talk to really any hardware. It's just something we can download code. So it creates a main function, and I kind of like it because there's nothing in it. I can understand it. So it kind of declares like a counter variable. Ints are 32-bit in ARM world. It's 32-bit, and it just has a forever loop where it increases the counter by 1. It kind of returns because it declared in the main that it returns an int, it returns 0, but we never actually get to here, and it doesn't really make sense to ever return from main, because what does that mean? Nothing, because our application, we always want to kind of loop around. We never want to leave main. So all this code does, as fast as it can, will increment this counter variable. So that's easy enough. So what we're going to do is build this program and then download it to the chip. So in the commander view, there is a build right here, or you can go up to project build all. I'll do that because I kind of feel comfortable. So what this does, since there were no problems, it doesn't look like anything happened, but I have all these green check marks here. Oop, I don't want to get rid of that. I'll come fix that later. We definitely want that part of the build. I'll go build selected files. Oop. All right, I'll fix that later. So once we build it, we want to debug it. So we can go up to this debug button. Looks like a little bug. There's also one in the commander view. We'll click on the one in the commander view, click debug. Now, one thing that's going to happen is you notice the screen changed. So Eclipse has this cool thing called perspectives. It's just a way, perspectives are just kind of, a way of storing how you want all your windows arranged. So whenever you debug, you want different stuff on the screen than you write code. When you write code, you want to see code. But when you debug, you might have other windows. So, it thought for a second, in the console window. But you notice it put a disassembly view, which is pretty cool, on the left. And I'm sorry, on the right. I don't know my directions. There's this debug, some information here about where it kind of stopped. Up here, there's actually a cool little window that where you can look up registers, all the registers in the device. You can look at raw memory, variables. So what I'm going to do is we're going to make the program go. Now this program also does, there's no real I/O, so it's pretty simple. So I'm just going to press go, and nothing's really going on here because it's running. Well, let's hit pause or suspend. Now you notice a little arrow, it stopped down here, and that makes sense. So it kind of looks at where the program counter instruction pointer's at. We can look in the disassembly view to see how it's actually doing the add. So this is kind of cool. It literally says here's counter plus plus. It loads register, adds, and stores a value, and then it branches back to this address. So that's kind of cool. Here's another cool part. You notice we can go up to the variables view and we see counter. And has a value, and it's very big because it works very fast. It kind of tells me where in memory it's at. So let's look at this, why I wanted to use a debugger. So I can use the step function. Step over just kind of means go to the next line. So as I click this, the counter just kind of goes up. And you notice down here, kind of finds a place to stop. Now, step into, had we had a function here, it'll actually step into a function and not step over. If we have function calls, we'll go over them and get a result. Step into actually goes into them. There's something called step return that if you're into a function, it'll return out. We can click restart. We can just see what that does. All right. It just starts over. It's going to reset everything. It literally is re-downloading the code. And what's kind of cool is we don't have to press go. We can just start stepping. Now, first line it gets to is right here, and it stops before the line executes. You notice when I highlight counter, it's to some weird value. Let's go step over. All right, counters at 0. That actually makes sense. Press go. So there's a simple application. You could modify this code, maybe make a different counter, play around with it a little bit, and go from there. So I'll click stop. Actually, we'll do a little quick exercise here. So we'll make a global variable here. We'll call int, Eli. I like to use Eli. And let's do Eli minus minus. So that'll make it go the other way. So I'm going to hit debug. Yes, it's going to rebuild it. Now, when I noticed the variables, because Eli was not local to the main function, it didn't pop up here. So how do we add Eli? What if I want Eli, that variable, to be up here? So I'm just going to click on it, right click, and there's a bunch of stuff here. Don't get scared. Just go say add watch expression. Expression in the watch is called Eli. All right. Gives me a new expression up here. All right. So let's go step. We'll do a couple steps here. Oh, look at that. Eli's going into negative numbers. Now, if we wanted our variables, you can actually right-click, say Add Global Variables. That's another way. And it brings up all the variables that are ever defined, global variables. So we can actually do it here. Look at Eli, get it in the variables view. So it's as easy as that. All right. So play around with it, and hopefully you'll come back and watch some more videos.